Hello. We'll study linear simple harmonic motion as projection of uniform circular motion on any of its diameter. Yes. So let us consider a circle with a radius A and center at O. Let one of the diameter be along the x-axis, say AB, and one of the diameter along the y-axis, say CD. Let small a be the radius of the circle. Now, if we consider any of the particle of mass m situated on the circumference of the circle and initially it is present on the x-axis. Now think of if you have a source of light placed somewhere over here. That has the light will pass on the object, and if a screen is placed on a diameter CD, then this particle at A will cast its shadow on O. This is called as projection of the particle at A on the diameter CD. Now suppose if this particle changes its position, say to A1, then its shadow will be somewhere over here. If we consider the projection to be, yes, the rays of the light coming parallel in this way. And so as the particle shifts on the circumference of the circle, the position of the projection will also shift. If M1, M2 are the positions of the foot of the are the positions of the projections, then when the particle will reach the C position, the projection will also reach the C position. And so, if we consider the particle moving on the circumference of the circle with uniform velocity omega, then certainly there will be the displacement of the projection of the particle on the y-axis, and it will move toward the point C. As the particle crosses and comes to the position say A3, the projection will come to M3, and now as the particle moves on the circumference from A3 to A4, we'll see the projection from M3 will move to M4. And so from this particular figure, we will come to know that as the particle performs uniform circular motion, its projection will perform simple harmonic motion on the diameter. So path of the simple harmonic motion will be CD. O will be its mean position, and so any of the position of the projection will give us the displacement in terms of y. And so in this way we can give the expression for simple harmonic motion in terms of the circular motion on this particular circle with center at O and radius equal to small. So let us see how it relates to it. Let us consider a circle with center at O placed on x-axis, y-axis passing through the center O perpendicular to x-axis, and the particle is going to move in anti-clockwise direction with uniform angular velocity omega. Initially, suppose if the particle begins from x-axis, then its projection will be on origin. With angular velocity omega, after time t, if it reaches the point A, then we see that this OA from point A, if we drop a perpendicular on y-axis, the foot of the perpendicular will at M. So this is 90 degree. So if this angle is omega t, omega, and the particle is moving for the time t, then the angle formed will be omega t. Then this angle will also be omega t. If this distance, which has been covered by, now we can say that the particle, which is the projection of the particle on the circumference of the circle, it moves up to point M. Yes. And so from the figure, in triangle OMA, sine of omega t will be opposite side OM upon radius OA. And so OM is equal to OA sine of omega t. So OM is y. This is equal to A sine of omega t. And so this becomes the equation of displacement when particle is moving on the y-axis. Now here the angle is omega t because the particle is starting from the x-axis, its projection is on origin, which is considered to be the mean position. Now suppose initially particle is at point A and it is at rest. So with respect to x-axis, angle say we'll take this point as S. SOA is angle phi. And this condition is at t is equal to 0. Now suppose from A the particle starts moving for small time interval, say t, and reaches the point B, and if this is with uniform angular velocity omega, then the angle casted over here will be omega t. So phi is the initial angle, and from here the angle will be omega t. Now if you drop a perpendicular over here, here you will see the angle theta. Angle theta is omega t plus phi. Now, if we apply the relationship, this distance is y, this is a because the radius of the circle. So, sine of theta will be again, let this point be m, OM upon OB. So, OM will be OB sine of theta. So y is equal to a sine of omega t plus phi. And so in this case, this becomes the expression for displacement for a particle performing simple harmonic motion. Now sure, phi is the initial phase, or it is called as the starting phase, or it is the epoch of SHM. Yes. And so when the particle will reach the y-axis, over here, the maximum displacement of the particle on the y-axis will be a. That is the radius of the circle, and the maximum displacement is called as amplitude. And so when the particle crosses, again the projection will start moving in downward direction, it will reach the mean position, and then it will go to the another extreme. And so in this way, we can consider the simple harmonic motion as the projection of uniform circular motion. If we consider the view from the top side, then in this case, for a particle moving on the circumference of the circle, projection will be on the x-axis. So, how we consider about the projection? If we consider the projection on the x-axis, then the particle is going to move along the path on the x-axis. If we are going to consider the projection on y-axis, the projection is going to move on the y-axis. But the expressions remain same. And so over here, now, as we consider about the simple harmonic motion, either it will be along the x-axis or it will be along the y-axis. If initially particle is, say, at A on x-axis with the distance small a, and its projection is on origin, say O, and say as the particle starts moving along the uniform angular velocity omega, the projection of the particle on the circle will be on the y-axis. We have seen the expression as y is equal to a sine of omega t plus phi. If the particle starts from point A on x-axis, then phi is 0. Then y will be equal to a sine of omega t. In this case, the projection is at origin. So this is the condition where SHM is starting from mean position. initially particle is present at origin, then the equation of displacement will be given by y is equal to a sin omega t if the path is along y axis. If suppose the particle is initially present on y axis. Now, if the particle is initially present on y axis, then the angle made over here with respect to x axis will be pi by 2. So the initial phase phi will be pi by 2. We have derived the equation as y is equal to a sin of omega t plus phi. Phi is equal to pi by 2. So equation becomes y is equal to a sin of omega t plus pi by 2. Now from this expression what we know, it is sin of omega t cos of pi by 2. Cos of pi by 2 is 0 plus cos of omega t sin of pi by 2. Sin pi by 2 is 1. So this becomes a cos of omega t. And so this condition becomes, if the particle is at one of the extremity, and say for instance it is at the positive extremity, and if the SHM is going to start with, then the displacement will be given by the formula y is equal to a cos omega t. So this is particle starting from mean position, this is for particle starting from extreme position. Now if the particle is initially present over here, so the angle over here is pi. So y is equal to a sin of omega t plus pi. So sin of omega t cos of pi plus cos of omega t sin of pi. Sin of pi is 0, cos of pi is minus 1. And so this becomes minus a sin of omega t. So in this case, the particle is returning back to the origin, back to the mean position, but the displacement is now why the negative sign? Because now it is coming toward the origin. In this case, sure, it was at the center, but then thereafter the shift of the particle is away from the origin. Here it will be towards the origin. Now when we consider about the particle present over here, the angle will be 3 pi by 2, and then the condition will come over here, and then 360, again the same condition will occur. And so as we see, the circle keeps on moving on the circumference of the circle with the phase difference of 360 degrees. The same condition will repeat again and again. So first cycle, second cycle, third cycle, there will be first vibration, second vibration, third vibration, and in this way we can say that the SHM is the projection of simple harmonic motion. Now over here, omega t plus phi, this is considered to be the phase of SHM. Now this gives you